Hello, I'm Beaufort. I'm a PhD student working on the MIMAC detector, and today I'm gonna talk about directionality and tracks in 3 dimensions in the keV range and even below with the MIMAC detector. This is the plan of the talk. I will start describing the detector and the experimental setup. Then we will move to directionality at high gain, and in particular we will look at the role of diffusion and we will describe simulations. And finally, we will talk about low-energy electrons and see how MIMAC can contribute in understanding the background and can search for action-like particles. So we start with the detector, and first let me introduce the principle of directional detection. So, as you know, the main direct projects searching for WIMPs are approaching the neutrino floor, which is a theoretical boundary beyond which it is not possible to discriminate between a WIMP signal and a neutrino signal. So far, the only known way to overpass this irreducible background is to use the anisotropy of the WIMP flux. Because we suppose that the WIMP would enter a detector with a favored direction. And then, if we are able to correlate this direction with the measurement of the direction of a nuclear recoil that is induced by a collision with the WIMP, then we can be sure that what we see is a WIMP, without relying on simulation. And then we can go beyond the neutrino floor. And this is the principle of directional detection. MIMAC is a directional detector. It is a gaseous detector, and which has the advantage that we can easily change the gas in the detector, so we can adapt the target mass, the spin, in order to search for some dark matter candidates. We operate at low pressure to describe the direction of the track, and with MIMAC we measure the energy of a particle, but also at the same time we reconstruct its track in 3 dimensions. We have an energy range that is adaptable and varies between 50 electron volts up to 30 MeV. And we use a micromegas with a pixelated anode. So a micromegas is a detector in 2 stages. One stage to drift the particles and one stage to amplify the signal. If a WIMP enters the detector, it can make a collision with one atom of the gas. So in our case, the main target atom is fluorine. The fluorine will recoil and will ionize the gas. The charges drift away under the influence of an electric field, and once an electron reaches the grid, it is avalanched, and we collect a signal both on the anode, that is pixelated, and on the grid. And this is what we get at the end. So on the upper left you see the measurement on the grid, which is the integral of the charge versus time, and from this we extract the energy of the signal. And on the lower left you see the measurement on the anode. So thanks to the pixels we have access to the position of the charges. And since we know the drift velocity of the electrons in the gas, and that we sample every 20 nanoseconds, we can superimpose those 2D images to reconstruct in 3 dimensions the track of the particle. And this is what is shown on the upper right, and here you see that there is a direction of this recoil. So this example is a measurement of a proton recoil of 6 keV in ionization. Finally, I conclude by introducing MIMAC, which is an accelerator of particle that is coupled with the MIMAC chamber, and that can send either ions or electrons of non-kinetic energy inside the MIMAC detector at a given position. So most of the results I will present later are obtained thanks to MIMAC. And here you see a picture, so MIMAC is pretty small. It is a tabletop accelerator, and here you see a MIMAC chamber. Okay, now I will present the results. I will start by describing the directionality at high gain. We are interested in low mass WIMPs, so they induce low energy recoils below 20 keV, and then the directional information is difficult to access. So the first thing is to operate at high gain in order to really detect all the charges. But something else that is challenging is that the tracks are short. For instance, a 10 keV fluorine will have a track length of about 320 micrometers, which is below the resolution of one of our pixels. So it means that a 10 keV fluorine would be seen as a point-like event in our detector. but actually it is not what we measure. Here on the right, you see a measurement of a 6 keV fluorine, and you clearly see that there is a direction here. And the reason for it is diffusion. You know that diffusion will enlarge the size of the primary electron cloud by about 1 order of magnitude. And in one hand, it distorts the signal, even though it is a Gaussian process. But in the other hand, it also magnificates inside the primary cloud. And actually, for tracks that are shorter than 1 millimeter, it improves our angular resolution. And this is quite a big concern, because usually people try to reduce the influence of diffusion. And here we observed in our detector that it seems to improve our angular resolution when we are looking at very short tracks, below 1 millimeter. For instance, this is the angular resolution we measured for several kinetic energies of fluorine between 6 keV and 26 keV. The measurements are in red. In purple you see the simulation. And this result has been published last year. So what you can see is that for kinetic energy above 10 keV, we measure an angular resolution that is better than 10 degrees, which is twice better than the requirements for a directional detector. And we are very glad of this result. Still, I have to say that the measurement has been performed in the optimal configuration, where we send the fluorine parallel to the electric field line. So now we have to reproduce the measurement with tracks coming in any direction. And we are working on that. But the thing is, here, this good angular resolution is accessible thanks to the diffusion. And we have also shown and published that we can reconstruct neutron spectrum at 27 keV, even if there is diffusion, and even if we are working with a large volume, and that interaction can happen in any places. So the diffusion will affect differently each track. It means that the diffusion can be under control in our detector. Okay, now I move to the central part of this talk, is the agreement between simulation and measurement. In this plot, you see the track length we measure versus the kinetic energy of fluorine, and in blue it is the measurement, in orange it is a simulation we performed with Garfield++. And as you see, the simulation and the measurement disagree. And actually at high gain they used to disagree. But this year I have developed a code that is called MIMAC, that is based on Garfield++, and that better models our detector and simulates the signal in it. So in this plot, MIMAC is in black, and as you see, it agrees very well with the measurement. So for the first time, we have a simulation tool that agrees and describes our measurement. The main difference between MIMAC and Garfield++ is in the way to treat the ions that are produced in the avalanche. First, because we look at the electric field induced locally by the motion of the ions, but mainly because we pay a great care about how those moving ions will induce a signal on the pixels of our anode. Because, as you know, the induced signal by moving charge is proportional to its velocity. And if you look at this plot that is a result from MIMAC, you have the charge induced on the anode versus time. And so you see the peaks coming from the electrons that are pretty intense because they are fast. But you also see a baseline here that is due to the moving ions. And actually, at high gain, there are many ions produced in the avalanche. And there will be so many that they will induce a signal that we will be able to see. And as you can see, when there is no longer a primary electron arriving, there is still this ionic signal contribution. And it elongates the signal we measure. It also distorts the signal we measure. And now that we have the simulation tool that describes it, and with that we understand this ionic contribution, we will try to find a way to deconvolve it and to see if we can improve our directional performances. This is what we are working on now. Okay, now I'll move to something a bit different. I will talk about low-energy electrons, because MIMAC can help in understanding such electrons that are part of the background, but also because it can be useful to search for action-like particles. In this measurement, you see a 12 keV electron that enters the detector on the upper right here, and that has a very curvilinear track. Now another example that is interesting because it is 150 electron volts, so it is a very small energy, And again, you see that even for such a small energy, we can reconstruct in 3 dimensions a track. But that's actually something that is very interesting when looking at such low energies. So here in this example, it is 250 electron volts, is that we see some population that appear in our histogram. If you look at the plot on the left, it is the histogram of the duration of the signal, and you see several populations, and each of them is correlated to a given energy that is Gaussian. And this we can interpret it as the fluctuation of the number of primary electrons. That we know follows a statistical distribution. Sometimes we will have I electrons, sometimes I plus 1, I plus 2, I plus 3. And this is what we think we observed here in this detector. And if we plot the energy of each population versus the number of primary electrons, we observed this linear tendency. And in this case, the slope is the gain per primary electron, and we have access to it with no need of W value. It means also that MIMAC is sensitive to the fluctuation of primary electrons, and then it is sensitive to each primary electron. Last thing I want to talk about is the search for action-like particles. You know that they are pseudoscalar and that they can decay into 2 photons, and when they have a mass in the keV range, their lifetime can be comparable with the age of the universe. And with MIMAC, we are mainly interested in Kaluza-Klein actions that would be produced in the Sun and that would propagate into extra dimensions. And actually, such action could decay into our detector, and the signature would be 2 photons emitted back to back and carrying the same energy, because they are non-relativistic. And such a signal is almost unique. There is almost no background in our detector that can reproduce it, which means that we could search for such ALPs with a very high rejection power. And this plot, it is not a measurement of ALP, but it is a measurement we perform with MIMAC by sending 4 keV electrons at a high rate in order to have 2 of them in the same time window. And what you see in the blue, so it is a measurement of the integral of the charge versus time. And in blue you have 2 bumps of same amplitude, which means same energy. And this is exactly what we expect to see if an action decay into our detector. So it is a proof of concept that we could detect ALPs in the keV range. And by simulation, we have determined that our detection of efficiency would be around 70%. I must now conclude this talk saying that MIMAC can search for a low mass WIMP with the directional information, and that can be used to discriminate the background, and at the same time it can search for action-like particles via the decay into photons. The directional information is difficult to access at low energies, below 10 keV, and we have seen that the diffusion could improve our angular resolution. And this is something pretty new, because usually people try to reduce the influence of diffusion. We say that for some millimeter tracks, diffusion could help us. Also, at high gains, so to see the low energies, there are many ions produced in the avalanche, and they will induce a signal on the anode, and they will elongate the track. And now we have a simulation tool that is able to describe it and that agrees with the measurements. So the next step is to deconvolve this ionic contribution and see if we can improve our angular resolution. And finally, MIMAC can describe in 3 dimensions low energy electrons down to 150 electron volts, and we are sensitive to each primary electron. So we say that we could help in understanding the background in a detector. Thank you very much for your attention.